sketch of the Bode plot for different systems. So for example here, if we have a GS and we have an output input, so this is defined as the output, this is defined as the input here. Okay, so here we're going to exercise different type of the G. So the first one, say GS equal to, say, simply a constant. So that is a constant gain for these systems. So the magnitude we simply plot is this is the log scale omega, and this is the magnitude. For this case, it's pretty straightforward. It simply is a constant gain here. Okay, and for the phase, so this is G, and in terms of the J omega. And for this case, the phase simply equal to 0. Okay, so that's the magnitude here. So that is the plot for this very simple system. And here I want to introduce you one more terminology, and we call it decibel. Decibel, hopefully, yes, decibel. Okay. A decibel is a measurement in terms of in the magnitude. By definition, 1 decibel is this. So say for this case, the system has a magnitude of K. And this one, this magnitude is measured in terms of no unit. There's a no unit for K. However, this one, if in terms of magnitude, we want to describe in terms of the decibel, in terms of the magnitude of the decibel. Okay, so right now here, I want to express it in terms of the dB. Okay, so converting the regular magnitude, a regular number, into a unit of a decibel is simply this. You take a log of this number and multiply that log with 20. In this way, after these operations, then you convert a regular number of the magnitude into the magnitude in terms of unit decibel. Okay, so for example here, then the magnitude of the system corresponding to here should be equal to 20 times log K here. You okay? And so for example, let me make up one. So for example, if say this level is 1, then that corresponding after the decibel conversion is basically that corresponding is 20 log 1. Basically that corresponding is 0 here in terms of the unit. Be good? Okay, so that means, for example, if we take this one, this value as a 1 here, so in terms of the decibel here, so that basically 20 log of 1 equal to 0 dB. So if you like to describe this in terms of the decibels, then this point, this level corresponds to magnitude of 1, basically corresponding is 0 dB there. You okay? Okay, so that one here, I basically help you to get familiar with the decibel, this term decibel here. Okay, so with this one, I can erase this and continue to the second type. The second one, we want to see for G is simply an integrator. Okay, so if G will be like this, then we can see its magnitude. And if we want to convert it into the decibel, okay, so basically that one is equal to 20 times. We do the calculation first and then we plot. Okay, so that one basically is the magnitude of Okay. And so on these situations, you can see basically this one we can convert it. That is 20 times the magnitude of this is how much? Simply is 1 over omega, right? Okay, so here from here to here, we simply apply the complex number, kind of the complex algebra. The magnitude of this equal to this. Okay, then we apply the log. So do you remember the log of 1 over a is simply equal to minus log a, right? Okay, so basically this is minus 20 log omega. Okay, and so for this case, we can have this is in terms of log omega, and so this is the magnitude again in dB. So now you can see the magnitude of this one basically is in a linear portion with respect to this. So that means the plot should be, this is the coefficients of this. So basically you can imagine this form is in terms of this template y equal to minus 20x, right? So y describing the magnitude in decibel unit, x is this one. So basically that is a linear straight line with the negative slope. So you simply draw it, okay? And here you can emphasize the slope equal to minus 20 dB per decades. You know the decades, right? For example, this is 10, let me make up 1, okay? So for example, this is minus 2 and 10 to the minus 1. So from here to here is called 1 decade. Okay? Decade is the measurement of the distance in the log scale for 1 order of the magnitude. Okay, so here the slope, take a good exercise in the decibel per decade. That is the one we measure here, okay? And so this one, basically the omega depends on, because this is in log scale, really depends on how you're going to place the vertical axis to, so it depends on where you put down. So sometimes this can be starting from, say, up to your applications. Could be starting from 10 to the minus 6 or 10 to the minus 5 or 10 to the minus 4, etc. Really depends on where you want to place your vertical, okay? Because this is in log scale of omega, so you shouldn't treat this point as 0. No, because log of the 0 basically go to minus infinity. Okay, good? So that means in terms of Bode plot, usually you have to know which domain of the frequency you are primarily interested, then you plot your things, define the range there, okay? So really depends on this point here. For example, say if this is the, say, 10 to the minus 3, for example, okay? Then this magnitude you can calculate, basically that is the magnitude of the G at J 10 to the minus 3, then you can calculate the numbers here. Okay, so times 20 log. Okay, so that is the initial value. You should be able to determine it. Okay, now we look at the phase. So for the phase, that is G J omega and equal to the phase of G J omega, that is J omega, right? So the phase of this one basically is the phase of the numerator minus the phase of the denominator. And so for this case, you can see that is 0 degrees and minus 90 degrees, right? Okay, so that means the phase is constant and minus 90. So that means if you draw it, and this is a log omega, and this is the phase of the GJ omega, and in terms of the unit degrees, so for example, you can label this one to here. So this is constant minus 90 here. Okay. So that is for the second case. Then we can gradually look into a bit more detail of more complicated systems. For the third one, for example, we look at the GS equal to a linear system, the first order linear system, for example, 1 plus TS. Okay, so that is a linear order, the first order linear systems for this. So now we simply calculate. So here we calculate the GZ omega, and then we put into the decibel calculations. Okay, so basically we plug in 20 log, and that one basically is 1 plus J times T omega. Okay. No, the magnitude. Okay. So we keep calculating. So the magnitude of this number basically equal to 1 plus T omega squared. Right? Okay. So this one we can simplify. So basically this one is minus 20 log 1 plus T omega squared. Okay, so from here to here, again, I already applied this formula. Okay, so this is the 1 divided by something, so I put a minus at the front here.
Square root.
Square root. Thank you. Okay, so square root basically is, yeah, whatever. Okay. And another formula, if you remember, A log of the A over M, whatever the index exponent basically is M times log A. And for the square root, that is to the exponent of 1/2. So basically here I take the second formula for this, then basically that becomes is minus 20 and multiply with this exponent basically become minus 10 and log 1 plus T omega squared. Okay? Okay, so we keep, then on the other side, the J omega, and that one basically is the, this one, 1 J times T omega, okay? So for this case is the phase of the numerators minus the phase of the denominators. Right, okay, so that is 0 degrees minus this one is arctangent and T omega. Okay, so here this is our formulas, and for our minor sketching, so basically I'm going to, based upon the two, then we can tabulate a few key numbers, and then we can trace the numbers to make the plot. Okay. So, for example, here this is the magnitude. The magnitude. Okay. So magnitude, let me copy that information, is minus 10 log 1 plus T omega squared. And our phase equal to minus arctangent T omega. Okay. So here I'm going to make a certain omega. And the first one is when omega is very small, extremely small numbers, we see what happens. Then T times omega pretty small. So that means you can approximate this number by 1. So log of the 1 equal to 0. So that is 0 decibel. Okay. And let me emphasize this is 0 decibel. And for this case, when omega is very small, basically it is arctangent of 0. Arctangent of 0 basically here equal to 0 degrees. Right? Okay. And the other one is I'm looking for is I think a more appropriate way is I should have the two together. So this should be T omega together. Okay, so that would be more appropriate. Because in this way, we deal with only single variable here. And in addition to the second one, let me skip on that one for just a few minutes. Let me go to the other extreme situation when T omega is so big. Okay, and basically this symbol means the order of magnitude larger, so that means at least 10 times larger. That is the numerical symbol here. So now for this case, if this is greater than this one, so the number in the parentheses can be approximated simply by T omega squared, right? So under this situation, that is minus 20, minus 10, log and T omega squared, right? So this one basically equal to minus 20 and log T omega. Okay, so that one in terms of the dB. And for the phase, when T omega is pretty big, so basically it's arctangent of a huge number. Arctangent of the huge number, basically that is equal to 90 degrees. Okay, if you remember the trigonometry, this is the theta, this is the tangent theta. Okay, so this is the 90 degrees. So when corresponding to a very huge number, that corresponding to theta is 90 degrees. Okay. So basically this curve is becomes cyclic from either way. Okay, so now we, in between, we can, if you like, you can place a few more, say 3 points, 5 more points. You simply name any number. For example, if you can say T omega equal to, say, 1, or T omega equal to 2, 3, 4, etc. to help you with more points, then you can trace the point. And in particular, of most of those numbers, we can try with this number and T omega equal to 1. Why? For that number, we do have particular, with this number, for this example, I can calculate here. So that basically is 1 plus 1, okay? So that means that is minus 10 and log of 2. And for log of 2, if you have a punch calculator, that is going to give us, I think, about 0.3. And let me double check. Yeah. Okay, so this number will give us is minus 3 dB. In the frequency domain, in the clock domain, keep in mind minus 3 dB, minus 3 decibel is a magic number. Is a magic number, and later when we approach the data, I will give you more evidence. Again, but right now you just keep in mind minus 3 dB is a magic number. Usually in the frequency domain, we like to have something available at this particular data there. Okay, so right now we set up T omega equal to 1. Yes.
Should that be negative 90?
Yes. Thank you. Yeah. Yeah. My mistake. This should be negative. Okay. So now again, for this one, when T omega equal to 1, so basically it's arctangent minus arctangent and 1 here. So this one basically corresponding is arctangent of 1 equal to minus 45 degrees here, right? Because if you look at the trigonometries, this is a 45 degrees, and this is a 1 squared too. So arctangent, tangent of 45 degrees equal to 1, or arctangent 1 equal to minus 45. We have a negative in ready from here. Okay, so with these things ready, then we can begin to plot. Those ones we don't need this anymore. So let me erase this one. So we can plot is this one. And And here, if you put the decimal as a unit here, that basically remind everyone this is on the 20 log scale of the 20 log of the whatever the magnitude. Okay. So now we simply place all the numbers here. So when T omega is very small, so say basically here, let me say here is omega equal to, I would say here we can put the T omega. Okay, we're simply using T to scale up. So in this way, when T omega equal to very small, so this is T omega equal to 1. Okay, this is T omega equal to 10. T omega equal to 0.1, etc. Okay, so when T omega becomes small, basically this is our 0 dB here. Okay, so that is the magnitude we calculated. And when T omega is very large, basically that is in terms of the slope is minus 20. Minus 20 of decibel per decade of this one. So basically here we can plot is something like this. When T omega is small, we know that is a constant, something like this one. Okay, so but when T omega become bigger, and that won't be the case. So here I kind of using the dashed line, but we know when T omega is small, that is for sure. So here we know the number is so accurate, so I use a solid line. Okay, and when T omega become very large, we know that these things will become something like minus 20 decibel per decade. And again, we know for T omega is large, then we can pretty much sure. So I use a solid line. But in between, when T omega is not that big, it's not that small, and so here we are not sure, so let me use the dashed line. Okay? And basically the dashed line indicating a kind of the asymptote for the curve. Okay, so here my drawing is not so accurate, but anyhow, and I can do it. And right now, we in between the situation, the transition in between, basically we can govern by our additional plots. For example, for this point, we know that number is minus 3 dB. So corresponding to here, we can label it. So see, this corresponding is minus 3 dB here. So we can label it this one here. Okay. So under these situations, again, I do it too quickly. I think, okay, everything so far so good, no mistake. The only thing I do so quickly is you see, this is the intersection of the two asymptotes, right? So that becomes the form a corner. So that one intersection corresponding to there, we call the corner frequencies here, okay? So probably you can visualize, you can treat this as the additional terminology. So corner frequency basically is at the frequency at which the two asymptotes intersect. So probably when system become higher order, we might have more than one corner frequencies. But for this case, we only have one. Okay, and I can tell you the corner frequencies is the frequency at which that is corresponding to minus 3 dB. So here I said my drawing is too quick. Okay, so here I would say, let me modify these numbers here. So this one should be 1, and this is 0.1, and this is 0.01. They are in equal space in terms of log scale. Okay? Sorry about this. Okay. So corresponding to here at the corner frequencies, we have the magnitude minus 3 dB. Okay, so basically from here to here, that is 3 dB below. Okay, so 3 dB below. So with that point be labeled, we can approximate our drawing manually. And by doing this, you simply, from the asymptotes, you simply gradually do the curving and passing that point and then approaching to the asymptotes there. Okay? So that is again similar to what we did in our locus. If you feel not so confident, you might be able is in this column you can add up 1 or 2 more points, and those points hopefully can help you to identify, say, here and here. That can give you more precise the manner drawing. Okay? Good? Okay, so you can take a break for